Oh, now I see it.
Okay, cool. All right, let me quickly share the agenda for today. So again, welcome to the review meeting. This time we look at the 1.1.18 release. And our first topic is from Dominic, which is actually one from 1.1.7, which we are presenting today about the CIDR overlap for seeds and non-HA shoots. Then we have Vedran, who's presenting a blog post about lowering the builds and saving costs. Then we have a new dashboard release, 1.80, which will be presented by Lucas. And finally, we will get an update about the in-place node updates from Shafiq and Ashish. Okay, then let's get started with Dominic.
Okay. Let me just try to share my screen here. Can you see the slides?
Yeah.
Okay. Okay. So again, this guy. We have CIDR overlap. Okay. This is actually from last time. So 1.17 release, but I got sick, so we have to do it today. Okay, so what's happening? The seed and shoot network ranges can now overlap. We are using a reserved range, the 244, which is a reserved range that usually isn't used or usable, so it's not routable. And this currently applies only to IPv4, because usually on IPv6 you don't have this kind of problem, and it only applies to non-HA shoots, so the non-HA control plane. But we are already working on the HA version also. So what's changing? Pretty simple. The pod range on seeds gets mapped to 241. The node service and pod ranges on the shoot gets also mapped to 242, 243, 244 respectively. But don't worry, you won't see any of those IP ranges anywhere else but the VPN tunnel. So your pod IP addresses, node IP addresses, and whatever, they all are going to stay the same. This is only for the VPN. And it comes with one limitation, namely that since we are mapping this to a /8 range, that your own networks can no longer be larger than /8, but I think that's about 16.7 million hosts for everyone, so I think that should be fine. And obviously, you cannot use the 240 ranges for your own networks. Okay, so why are we doing this? The end goal is basically to disentangle the networks between seeds and shoots completely, so you can have the situation that you have two pods, one on the seed and one on the shoot, and both can share the same IP address. Technically, when we zoom into this the VPN tunnel, this is solved by doing a double NUT. So we NUT the source as well as the destination IP address to one of these 240/4 ranges. And then we undo this nutting once we leave the tunnel again and go back to the original IP address. You may wonder, what if there's a second pod in the seed that has the same IP address as the shoot pod? How does the API server know which way to go? And the solution is we are using this feature called egress selector, where we tell the API server, okay, if you want to go somewhere in the control plane, you just do your regular routing stuff. And if you want to go anywhere in the cluster, you go via a proxy. And this, I'm going to show you right now how this all works. You can see here I have provisioned one shoot called overlap, which has a pod range 1064/11. If we look at the seed, you see that the pod range of the seed has the same range, 1064/11, and it still works. So it's a non-HA shoot, like I mentioned, but we now have this situation where you can have this. I have two terminals here, one on the left, which is the seed, and one on the right, which is the shoot. and I'm going to show you how this technically is implemented. When we step into the VPN server on the seed, you see there's two containers. One is the proxy I mentioned earlier. That's going to be important now. And one is the VPN server. If we take a look at our IP setup here, we have this nice ETH0. It has an IP address from the seed pod range. And we have this tunnel device, which is used for VPN. It has a IPv6 IP address. But that's only used for the tunnel communication between the VPN client and the server. Now we can take a look at some black magic we did with IP tables. Let me just bring up this here real quick. Okay, now to explain this, we need to know that this Envoy proxy that is used by API server runs as a specific user. It's a non-root user, which has a specific user ID, and we can leverage this fact. Also the fact that this Envoy basically terminates the connection coming from API server and reopens a new connection. So this means this new connection will go through the output chain, where we can then define a rule that basically says, okay, if you want to go in the pod to the pod range, even though it's my own pod range on the seed, but the user ID of the socket that opens this connection happens to be the Envoy user, then you don't use that destination. Instead, you do a net map, which is basically just a very convenient way of DNAT. We net map this destination range to the 244 destination range, and we do the same for services and nodes as well. So now this is done. So we have nutted the destination IP. Now the Linux kernel will take a routing decision. So it looks at the route table, and now we have conveniently here these three ranges that tell the Linux kernel, okay, if we want to go anywhere here, we have to use this tunnel device. So this leaves the host, it goes into the VPN tunnel, and as it's leaving, it takes another look at IP tables in the post routing chain, where we have another rule that says, okay, if you want to go out this tunnel device and your source IP address is also the pod range, in this case, it's the seed pod range, then we map this pod range to the 241 range. So now we have mapped basically, we have a 241 IP address talking to a 244 IP address inside the tunnel. Okay, now this IP packet leaves the host, it goes out into the VPN tunnel, and it enters the shoot side on the right here. Let me just go into this pod. Okay, now here we have the same setup, ETH0, same range, a different IP address in this case, and we have this tunnel device. Here we basically do the opposite of what we just did. Just bring up this nut table here. And you see here, in this case, we have the pre-routing chain in the nut table, which means packets coming in, new connections coming in. And we take a look at the TUN device again and check, okay, if your destination is 244, like we just mentioned, then we basically undo this nutting and get it back to the 1064/11. And now we have a 1064/11 destination IP address. Then again, Linux will look at the routing table. Okay, we go IP route. And now here we see there's no entry for this 244 range again. And we have no entry for 1064. So it has to choose the default gateway, which is right because it's just our own subnet and it will go out through ETH0. And as it's leaving, again, we have the post routing chain where there's one entry called masquerade, which just basically means source net from my local device. This is also very convenient because it will hide the 241 IP address we set in the source nutting on the seed, and will make it so that in this case on the shoot side we have 1064 64/11 talking to 1064/11. So from the pod's perspective that gets traffic, everything is just normal traffic coming from some pod inside its own subnet. So the guy will respond, and now we have conveniently contract in both Linux kernels, making sure that all of the reply packets from the pod will just find their way, and we don't have to reapply any more legacy IP table stuff, because contract will know how to find its way back to the source. Yeah, I think that's basically it. It's pretty neat. It works because we have this envoy in place. Yeah, I think that's about the demo. Any questions? There's a couple.
Stefan, with a raised hand or wrong button?
Yeah, Stefan here. Was there any specific reason to choose IP tables still and not NF tables?
Yeah, we're basically tied to what is used in Kubernetes. So if the CNI we are using is still using legacy, then we also use legacy. We basically go lockstep here. But you're right. It's about time we move to NF tables in general.
All right, then I guess that's it. Thanks, Dominic.
Thank you.
And next one would be Vedran with a blog post presentations.
Sure. I just see Jan had still a question.
Oh, yeah, thank you very much. I was just curious about the internal mapping, because just for me to understand this correctly, that means the C cluster is basically getting a different representation of the same IP address of the sorry, I lost the bot. C cluster from the client cluster, right? Basically, it's like, is there like a database where we keep track of this mapping, or how do we not mix this thing up? Because I feel like we have 10 times the same IP subnets, or do I get this wrong?
So in the seed, every shoot gets their own control plane. So every shoot has their own VPN. So you don't have to sort of remember which shoot has what IP address, and they all internally use the same range, so it doesn't matter because the VPNs are separate, so you don't have to any like crosstalk between two shoots or whatever.
Just, I try to sound stupid right now. Why not using IPv6 instead?
Yeah, we explored that. The problem is there's currently no easy way in the Linux kernel to do NAT 6.4. So when you put everything in a NAT in a IPv6 IP address, so you could basically put the IPv4 in an IPv6 IP address and then undo the thing on the other end. The problem is this undoing stuff, the nutting, is not part of the Linux kernel yet. So you would have to use a userland service, and there's currently some of them with varying grades of maturity. Some of them even use kernel modules that you would have to load. So it's unfortunately not a thing that you could just do in Linux natively. So that's
just
the problem
maybe
right now. Not
understanding because when you use IPv6, why you need NAT. I mean, the reason we use NAT is because the address space is insufficient, right? But if you IPv6, that should be no problem, right? I feel like when you want to use NAT 64, that's just the wrong solution for the problem. Or
yeah, but you have a choice.
having...
You can use IPv4 in your shoot, so you need IPv4 support. right? So your pod IP will be IPv4. So somehow you need to address that.
So basically, you mean the translation from IPv6 down to IPv4, where you basically have an IPv4 gateway for that, and you say that this feature is not working properly.
Yeah.
Ah, okay. Yeah, thanks.
All right.
All right, then let's continue with v1.
Thanks. So we published a new blog, leaner clusters, lower bills. This is about a few things that we did over the years to reduce costs. It focuses predominantly on compute costs, but it also talks a little bit about some other things. And of course, I'm not reading it out. So wait a second. So when you read it, we basically start with the most reasonable things. Get a hold on your cloud provider builds, understand them, implement some regression monitoring. Over the years, we have had some regressions. For example, in the networking area, it's really difficult to see that unless you have this kind of monitoring, because some little change may end up costing you a lot of money, especially in networking, because that's the most intransparent of the different cost factors that you have. What we also learned actually pretty early on is have good controlling on your reserved instances, saving plans. We are talking a little bit about that, but we don't go very much into depth here, because this is covered by our employer. Has sophisticated tooling. Probably other companies have similar tooling. So look at that and find the break-even point where it's reasonable to purchase them. And then we also talk about a few more things. Of course, the costs that can be most easily cut are costs that are unnecessary. So we have hibernation feature. Finding non-hibernated clusters in development, for example, is something useful. Often clustered, often resources that can happen during development. So it's not that Gardener leaks resources, but during development, you do certain things and then you forget about the resources that your half-developed code has left behind. And we have also implemented a tool that you may be interested in. Let me open it quickly. Inventory, Gardener inventory. And if I go to the design goals, then basically the idea is here that there are different data sources that collect information and put that into relational database tables and link those. And then you can find out, okay, on the ledger, I have these resources. I expect certain other resources at the cloud provider side to exist. And then I'm trying to match those and find out what is not, what is, for example, on the cloud provider side that shouldn't be there. This tool is agnostic of Gardener, so it doesn't have to be Gardener resource, can be your own ledger, can be your own resources that you create. You just need to plug in the data sources, and then you can basically get notified about any things, about any discrepancies between what you're expecting and what is actually there. So this helps also to track down or to reduce the costs. If you are operating Gardener, then management of your seats is of course very relevant, because most of it happens there. We have managed seats. We didn't go yet to the degree to have managed seat sets. So I linked also the different proposals. So managed seats are implemented, managed seat sets not. So this is still something that you need to manage yourself. So not really manage the seats, that is taken care of, but how many seats you have, where you have them. And of course, micro seats are something that you shouldn't have, unless of course for regulatory reasons. You can use control plane migrations to relocate control planes of your shoot clusters, so to compact seats. This is another point where you can save some money. You just need to make sure that the control plane is not around the world somewhere else from the worker nodes. There are a few networking things that we worked on in the years. So this is a very old one where we basically centralized our ingresses, that we have fewer load balancers. This is a cost driver. We implemented registry cache extension for shoot clusters, but of course we use it also for seed clusters. So this avoids repulling images again and again. With the introduction of HA control planes, of course, we had also the topic of how to reduce the cross-zonal traffic. So we implemented topology-aware routing. We are talking in the blog a little bit about these things. And of course, implementing controllers. I mean, we are in this business for quite a long time, but we see users with very inefficient controllers that lead to unbalanced API server load. And this is really bad. So whenever the load is unbalanced, because everybody uses the vertical pod autoscaler. Vertical pod autoscaler targets the requests based on certain configuration we come to later, and applies the same recommendation to all of the pods. And this is, of course, a problem if you have imbalance. You can end up, because of, I don't know, a silly controller causing one API server to run at 16 cores or whatever, that all the other API servers that wouldn't need that kind of CPU power also get 16 cores. This is a major cost driver, API server specifically, because it's one of the largest component. All right. We don't go into this architecture diagram. I just wanted to show it because everything in Gartner is basically Kubernetes. So you have tens or hundreds of seed clusters, hundreds, thousands, tens of thousands of root clusters. Everything in the end runs as a pod. So when we can optimize how we place our pods on the nodes and which kind of nodes we have, this is the main. This is the most useful thing to do to reduce the costs. Let me quickly go and quickly go here. We have a little bit of tooling that I can show you. I mean, this is a dev landscape. I cannot show you productive landscapes. This is basically looking at a particular seed cluster, in this case, an AWS seed cluster, analyzing the nodes. And a few key metrics that are interesting here are, for example, these relationships between, for example, core to gigabyte. This drives which kind of machine type you would like to choose. Something like 1 to 6 is very inconvenient because usually cloud providers have ratios like 1 to 4 and 1 to 8. 1 to 6 sits right in the middle, so this is not good. You're either wasting CPU or memory, depending on which machine type you've selected. It also analyzes different other things like volumes to gigabytes, pod to gigabytes. And you see here also reserved CPU and memory. You want that to be somewhere around 100% requested CPU. So how much of the CPU is requested, how much of the memory is requested. And something like this is not good, but it's also not really bad. This is how much of the attachable volumes are consumed. There are a few more things, but I just pick these. For example, volumes is more of a problem if you go to Azure. On Azure, you see a few nodes at 100%, a higher rate there. So there you hit the limit much faster, and you are much more restricted in which machine types make actually sense for you in comparison to something like GCP, where you have much more attachable volumes. There it doesn't matter. We also have dashboards I quickly wanted to show you, just that you get a feeling on what we are looking at. So total CPU and memory, yes. Used CPU and memory, again, this is a dev landscape, so the numbers are pretty terrible, but you can still see some things like, for example, total CPU. Obviously, we did hear something around that time and reduced the number of CPUs. You see that used capacity CPU went up. Memory, something bad happened, went up. But more interesting than the kind of used from capacity are these metrics here. So what kind of a node has a certain allocatable CPU and memory, so which is basically capacity minus whatever is reserved. And you want that to drive up, and there are different means to drive up this, so the request from allocatable as compared to the usage of what you have requested for your individual pods. So this is of course nice if you can see, okay, we are going up here, requested from allocatable, requested from memory, had this dump, but went also up. Used from requested is how much CPU your pods really use. So these are interesting key metrics, and the reservations as well. So you see here that a year ago or so, there were problems. So it was heavily under-reserved and then over-reserved. And you want to target something like 100%. I mean, this is what you ideally want. We also look at in our landscape, so what are the filling rates and by which resource are you bound? So if you're at 100% CPU, it doesn't matter that you have memory left because it won't be used. and also certain other things like I mentioned already, the CPU to memory ratio, which drives your decision about the machine types. So the blog speaks about that and also mentions a few of the key things you can use to improve the cost. So packing the pods onto the nodes influences your request from allocatable, and there is bin packing, configuration for kube controller manager and kubelet to host more pods. You need also to adapt kube reserved, autoscaler configuration, how you can tweak this one. And then there is this other aspect, which is about use from requested, which is right-sizing the pods. Mostly it's VPA. We have made some learnings there, things how you can improve that utilization. So target CPU percentile, memory percentile. We don't have, unfortunately, the time to go into detail. CPU histogram, decay lifetime, recommendation lower bound. This makes you react faster to changes. There were a few more things, like you should not have too high min allowed, must be reasonable. Max allowed is something that we contributed upstream, where you can basically say, okay, I want in general max allowed to be cut at a certain number, and this then should ideally match your largest machine type, so that no recommendation is ever made that cannot fit on a node, which is a practical problem. We are talking about pod requests, but actually we are referring to another guide that we have on pod autoscaling best practices that you can dive in. It's a very long documentation on what you can do to reduce costs. All right. And then about the machine types, I mentioned already a few things just quickly. So the considerations that you might have when you choose the machine type is the generation, CPU to memory ratio. There are some hidden constraints, network throughput, attachable volumes, and then of course the t-shirt size. So this is these are the things you are mostly concerned with. In the past, we did a kind of manual, and now we have, for us at least, some automation in place, which is using exactly these things. And I can briefly show you how this would look like, or how this looks like. So this is looking at a particular seed cluster, and there is kind of the current ranking of machine types that make the most sense. And this is then the recalculated one based on the current data, and you recognize the same things that you have seen already: allocated CPU, allocated memory. What are the values here? What are the reservations? And it makes also new recommendations for the reservations. But most importantly, it ranks again the machine types. You see here the different machine types, and it basically computes kind of the load, CPU, everything into gigabytes, and decides based on this uniform on this unit how much of a machine would actually be used, puts that into relation to the machine costs, decides the efficiency, and then basically redefines the worker pools for your seed with the priorities. Priorities can now be specified in place in the chute. So you see that many things that we did in the past came also out of our own drive to reduce the costs. A lot of that is directly available to you. Some things, because you are, if you're operating Gartner yourself, is then still your responsibility. But a lot of the things can be already used off the shelf. Right. Yeah, there is no time to go into more detail in regards to kube reserved, but this is also an important point because if it's too low, then you might have problems with kubelet container runtime running out of CPU, for example, and it's quite kind of difficult. There is a kubelet stats API that you can use and that our tooling is using to basically derive the more reasonable kube reserved settings. Cloud providers usually have very workload naive settings, and we look at our concrete workload to understand it. There is also a little bit about looking ahead, so addressing this load balancer, this load imbalances. Depends, of course, on the clients and a few more things. Yeah, if you have the time, please read the blog. It's a very long one. Thank you very much.
Thank you. Any questions up front?
No question. Just thanks to writing all of this down. This is very helpful.
Hopefully. Thank you.
Right, then thanks, Rekan, and over to Lucas for the dashboard 1.80 update.
Yeah, let's share my screen. Okay, so I want to give you some update on the main features that we released with our 180 release. So the first thing I want to show you is that we changed the former called secrets page. It's now called credentials page, and we now support credential bindings. As you probably know, there are now next to the already existed secret binding, also possible to create credential bindings in Gardener. And credential bindings support secrets and workload identities. In the dashboard, we now refactored the page here, and you can see that there's now a new column called kind, where you can see what kind of credential binding we are looking at, right? So in this case, this is a secret binding that's referencing a secret. And here it's credentials binding that's referencing also a secret. And as you can also see, now that we have different resource types, you can also have name clashes. In this case, we have two AWS secret resources. One is a secret binding and one is a credentials binding. For this reason, we introduced this kind here, and this icon, and everywhere in the dashboard that we now show such binding name, we also show the icon next to it so that we can always see what kind of credential you're using. So for example, if I go to a cluster here, you can see that in this case it's a secret binding. And also if you create a new cluster, you can see here in the drop down, we can also always hover and look at the tooltip, or you can differentiate also because the secret binding is filled while the credential binding is not filled. And you can also now with this change also use workload identities directly in the dashboard. However, right now with this release, we do not support editing or creating them, but you can use them. So another thing I want to show here is that there can be name clashes, but there can also you can also reference the same underlying secret, right? So in this case, we have two resource bindings, one a secret binding, one credential binding that reference the same secret. And if you now edit one of them, we show a hint to the user in this blue box here that this underlying secret is also referenced by this other secret binding. And if you change it here, it will also have impact on the other binding. What you can also see here is that now in the edit dialog, we load the data of the secret into the fields. So previously you had to replace everything. Now you can edit the single fields because we pre-fill it with the current data. So you can only update what changed. The same information is also shown if you try to delete a secret binding. In this case, it's a credentials binding that you want to delete. And you get the information that the secret is also referenced by the other one, the secret binding, but it will not actually delete a secret. And it's safe to delete it in this case. Yeah. What else? Yeah, we also added handling for the case when a secret or a reference secret is not there anymore. In this case, we have here a secret binding that references a secret that currently does not exist. We align this with the handling that we also have for members, that service accounts. So if you try to edit this now, you get information that the secret is missing. And if you would now add or update it, it would be recreated. Okay, so the next thing I want to show you is the things we changed on the cluster page, or the clusters page, the table here. We reduce the height of the rows so that now you get more information on one page. We also remove the paging. So in this case, we only have 2 clusters. I will show a large list soon. And we also worked on the different things like the workers or the ticket labels and things like that can grow to a large number of items if you expand it, so that we can ensure that the height of the rows always has a fixed maximum height in order to allow the list to scroll evenly. Because if the height or the height of single items gets too large, the re-rendering of rows would not work as designed. I can show this if I switch to another project that I prepared. Let's go to this one. You can see that we now have way more clusters. We have like 500 clusters. Of course, it looks a bit empty here, no readiness and stuff, because this is a local setup where no controllers are running. But I think you will you get the point. So you have a lot of information on this page. You can scroll. The rows will be rendered on demand, and you can have all on one page. And also, as I already mentioned, we worked on things like the workers, that if they grow to a large number, you can scroll here so that the single rows don't get too large. And okay, other than that, yeah, we also introduced now reactivity for projects. So as you may know, the only resources that are currently being watched in the dashboard frontend are shoots. So you get real-time update for shoot resources. All other resources are only loaded when the page reloads. And we are working on making all of them getting real-time data. And the first resource now that we changed to receive real-time data are projects. And I can show this here in the project list. I currently have these projects. And now I will create a new project. And you can see that it appears here without reloading the page. I can navigate to it and do things in it. And now if I decide to delete this project, it will disappear, and we have handling for it that the project is now gone, and you can navigate to a different project. Of course, this for project is now maybe not that big step forward, but it's a preparation to get all the other resources like seeds and the garden resource and stuff like that as real-time resources in the dashboard. Yeah. So basically, that's it. There are lots of more small features that you can read in the release notes.
Nice, thank you. Any feedback so far? Lots of applause. All right. Cool. Then let's go over to our last topic for today, the in-place node updates.
I hope my screen is visible and I'm audible. So today, me along with Shafiq will be presenting DEP 31, which is in place node updates of suit clusters. So what was the motivation behind that one? So in Gardener, certain changes to the worker pool configuration can trigger a rolling update, which can lead to recreation of the node, that is replacement of the node. So this can be challenging for physical machines or bare metal nodes, which are not as interchangeable as the virtual machines. Because of the reasons like longer boot time, generally physical machines have a longer boot process, and cleaning up or erasing of data on the physical machines generally involves a longer time. And physical machines also comes with basically comes with locally attached volumes, which cannot be easily moved or reattached to the other machines, which is not the case in the um, networkly attached VMs. Limited interchangeability, that means the physical machines generally are bigger in size and limited in numbers. So it is not very reasonable to easily replace those physical machines. So what actually is the update strategy? Update strategy actually defines how machine controller manager, that is MCM, will orchestrate the update process of a worker pool. So basically in our Gardener, we support 3 update strategies: auto rolling update, auto in place update, and manual in place update. Currently, in place updates are kept behind in place node update feature gate. So in order to use auto in place update and manual in place update, we'll have to enable this feature gate. Okay, so what is auto rolling update? This was already present with the name of rolling. We just renamed it to auto rolling update. This is the default update strategy, where upgrade will be done in a rolling fashion, just how the pods are updated in a Kubernetes environment, which are backed by the deployment. Here, worker nodes are terminated one after the another, and those are replaced or with the new machines or the new nodes. So what happens in the auto in place update? How it is different? So basically, in any of the update process, there are on the top level there are 4 actors involved. One is user who initiate the update process. One is machine controller manager, which orchestrates the update process. One is node on which the actual update is happening, and one is Gardener node agent, which carries out the actual update, which actually updates the node. So in case of auto in place update, once user makes the changes, machine controller manager will go ahead and it will label all the nodes with all the nodes under their worker pools with candidate for update label. So once that is done, it will select nodes for update. It will label them with selected for update, and all the nodes with label selected for update label will be cordoned and trained by MCM. Once the train is complete, it will mark that node for ready to update by updating the in-place node condition to ready for update. On the other side, GNA will be waiting for the in-place update node condition to be ready for update. Once it sees that condition, it will go ahead and it will apply the update on the node. Once the node is updated, GNA will restart all the pods on that particular node and then set the update result label on the node to be successful. And then once the MCM sees that label to be present, it just uncordons the node, and then that node is again ready to be schedulable, ready to schedule the pods. So that is auto in place update. Here, everything is done by orchestrated by a machine controller manager. There is no human or manual intervention needed. So why do we need manual in place update? Suppose you have 5 nodes in a worker pool and you don't want to update all the nodes at once. What you will do? For those scenarios, we have manual in place update where user has the user can orchestrate which node they want to update at a particular amount that time. So here also, whenever user will change the spec, MCM will mark all the nodes under that worker pool with candidate for update. And then here, MCM will wait for selected for update label on the node. It will not just go ahead and select and mark all the nodes for selected for update. This is a major difference between auto and manual in place update. So once user selects a particular node, by labeling the node with selected for update label, MCM will go ahead and then proceed with the rest of the update process as it was discussed in auto in place update. That is, it will cordon the node. Once the drain is complete, it will mark that node for ready for update. Then GNA on the other side, which is already waiting for that ready for update condition, it will apply the update, restart all the pod, mark the successful label, and then MCM will uncordon the node and that's how the node will again be ready to schedule the pods. So this is the basically major difference where the user in the manual user can select a particular node. They don't need to select all the node at once. They can select whatever time suits them. So what are the features for in-place update? In-place update generally supports all the rolling update triggers, except there are a few obvious ones. That is the machine image names, machine type, volume size, CRI name, and then node local DNS enabled field. Apart from that, in-place update is also supported for credentials rotations, that is certificate authority rotation and service account signing key rotation. Moving it. So what is actually happening on the MCM side? So in the rolling strategy, whenever there is a change, machine deployment changes, new machine class is created, new machine set is created, which in turn will create a new machine, and it will delete the corresponding machines from the old machine sets. So machines are created in the new machine set, and machines from the old machine sets are getting deleted. So that's what happens in the rolling strategy. How it is different in in-place strategy. So in place a strategy, whenever there is a change, new machine class will get created, new machine set will also get created, but new machines will not be created. Instead, we are just transferring the owner reference from the old machine set to the new machine set. We are no longer deleting the machines. So the underlying VMs remains intact. There is no deletion of the VMs. Only the owner reference of the machines are getting changed here in case of in place strategy. Okay, so API changes. So in the cloud profile API, a new field in place update has been added under the machine image version. So which has two fields. One is supported, which indicates whether that particular machine image version supports in place strategy or not. And second one is minimum version for upgrade, which specify the minimum image version needed in order to update to that current version. So I'll explain that with a simple example. So suppose we have a cloud profile here. Here you can see Garden Linux has 1630, 1632, and 1634. All of them are supporting in-place update that can be seen from the supported field. And there is also minimum min version for update field is set for all of these versions. So suppose if you want to update from 1630 to 1632, as per the cloud profile, it is allowed because min version for update is 1630 and we were on 1630 and we are upgrading to 1632. So this is allowed. But what if you try to update from 1630 to 1634? As per the cloud profile, it is not allowed because 1634, in order to upgrade to 1634, min version for update is 1632. So this change will be rejected. So in order to upgrade to 1634, first you will have to transition to 1632 and then from 1632 to 1634. I hope this clears up the field, the requirement of the field min version update. Okay, moving ahead. Shoot API. In the Shoot API, we have introduced a new field called update strategy for all the worker pools, which is under spec provider workers. And this can take auto rolling update, auto in-place update, and manual in-place update as values. So 3 values are possible for this one. And there is also defaulting for that. If you will not specify any field for this one, then any value for this one, then it will be defaulted to auto rolling update. And in order to specify auto in-place update and manual in-place update, you have to enable the feature kit, which was already discussed. That is in-place node update feature kit. Okay, operating system config API. Under the operating system config status, we have added a field called in-place updates, which has OS update command and arguments. So OS extension generally should populate this field with the necessary update command. So whenever the machine while upgrading to machine image updates, while doing the machine image updates, GNA will execute this command, which is present in the OS update.command to for the OS updates, for the machine image updates. Okay, so with this, I'll hand over to Shafiq for demo.
Share my screen. So yeah, let's get into the demo. So I already have one CIDR and shoot setup in the interest of time. So if we quickly check the YAML of the shoot, we can see that there are three worker pools. So the first one is called auto, and we have some kubelet config, we have Kubernetes version, also machine image configured, and the next worker pool is called manual, and with strategy manual in place update, and similarly kubelet config, Kubernetes version, and machine image, and also one more rolling worker pool with update strategy rolling update. So let's quickly go into the update. So I will update the Kubernetes version for the first worker pool, also the kubelet config. And for the second worker pool, again, Kubernetes version and kubelet config, also machine image. And yeah, for rolling, maybe I'll not do anything. Let's try and apply this change. Yeah. So we go to this pane, we can see that the machines, there are like two machines for auto, one machine for manual, and two machines for rolling worker pool. And similarly, the machine sets, also the machine class. So as explained earlier, new machine sets should be created for the in-place update strategy worker pools. Also, new machine classes will be created, but the nodes and machine should stay the same. And quickly checking the machine image version for the manual worker pool. So we can see that it's in Garden Linux version 1830. Okay, now we can see that a new machine set got created. And here the nodes, we have this in place update condition. So this will be first candidate for update, and MCM was too quick. So it updated it, drained the node and marked it ready for update. And GNA should, after the update, it should change it to update successful. So this is happening so fast now, like don't get carried away because there are no workloads running on these nodes. So the drain is very quick. So everything is happening so fast. And it has got now moved the new machine set now, one of the machines, and the next machine should get selected anytime soon. So we can see that the status has now changed to in-place update, and here the condition should change ready for update in a bit. Sorry, it was this one, my bad. So now the update is successful. It should also get moved to the new machine set. Yeah, so it has now got moved to the new machine set. But for the manual, we can notice that nothing has happened yet. So as explained, user should manually select the node for update. So let me select this manual node for update. And we can see that from candidate, okay, that also got drained so fast. We did not see the selected for update, but yeah. So this update should take a little bit time because it involves machine image. So in the meanwhile, I can again go back to the shoot. So if we do a YAML of the shoot, we can see that in the pending worker updates, under the in-place updates in the status, we can see that there are two worker pools. One is auto in place and one is manual, which is pending for update. So this is to keep track of the current update and to prevent subsequent updates, because that can cause skipping kubelet versions or machine image versions, etc. So we don't want to do that. So for that, we are keeping track here. And there is also one constraint added in the shoot, which says that some worker pools in your shoot with update strategy, manual in place update are pending update, which because even if manual in place workers are pending update, shoot reconciliation will be successful and it will continue with normal operation. But to keep track and notify the user that some updates are pending, we have introduced this constraint. So this is one thing. And in the meanwhile, this is getting updated. We can check the already updated nodes. So I will check the node agent logs for. Okay, sorry. So here we can see that first it was waiting for the in place ready for in place update condition. Then it started the update, and if we see the logs here, we can see that there was no OS update for this worker pool, but kubelet minor version was there, kubelet config was there. All those were applied, and then after that, the node was marked with update successful label. And we can also see here for that node, previously it was 1.30, it got updated to 1.31 now. So yeah, so kubelets got updated, but for the OS, yeah, it takes a little bit time. And in that time, I can explain the OSC. So if we quickly check the OSC for the manual in place update. We can see that in the status, the OS extension have added the OS update command and also the argument. So this command is basically just a script. So if I check the script, so it just calls this Garden Linux update tool, which is what the folks created, which downloads a new UKI and boots it to the new UKI. So if it fails, then it tries to return some exit status, etc. for the node agent. Yeah, and if it succeeds, then it just reboots the new version. And if we go back, we can see that the update is already successful. The machine has started now running. So let me just quickly go into the node and do a check the version, and we can see that it has now gotten updated to 1861 from 1830, and all this happened in place. And yeah, the shoot is now fully reconciled. Yeah, that's pretty much it. Sorry for going over time. And yeah, back to the film. Any questions?
Nice. Thanks, Shafik and Ashish. We have 1 minute for questions. Be free.
Just a comment, really great seeing that in action. Really nice.
Maybe one question then. What's the plan for the feature gate, or what's the general feature status? What's the plan for the promotion of the feature gate?
Yeah, now got only AW, like the extension needs to be now released with the changes. So we are waiting for that. So once all the extensions are released, then yeah, we can go with enablement and etc.
Okay. Shivani, any final words?
No, nice demo. This retry mechanism of this tool, right? That is now inbuilt in the tool, and the script doesn't do the retry. So any other OS extension implementing should understand that retry has to be built within the tool.
No, script does retry if it's network problems or some transient things.
Okay.
Yeah, if it's like we have the script should take care to return the error so that node agent knows whether it's retriable or non retriable. Yeah.
Okay, cool. But nice script and nice demo. Thanks.
Okay, folks, then we are out of time. Thanks to all presenters. Thanks to everybody for joining, and then we meet again in 2 weeks. Bye-bye.
Thanks.
Thank you.
Bye.
Bye.
Bye-bye.
Bye.